Hello again, Year 7. Here we are, new week, and it's a new topic, electricity. This is our last topic for this term. I think we're just about going to make it there if we work well, which I know you always do. Amazing to think you're nearly Year 8 already, isn't it? So we've got a starter on the first slide here, which is a quick bit of revision. I'm sure you'll all be amazing at it. Just draw the table, write down the particles and their location, where they're found in the atom, and what their charge is. Remember, I'm sure I don't need to tell you, but I will anyway. You can pause the video while you do this. And here are the answers. No surprises there, I'm sure, because you are brilliant. If you weren't sure about anything, just double check it. Make sure you've got it right. You need to know this for later on. Our objectives today, we've got a little bit of revision, first of all, of the charges, particles and locations of the different particles in an atom, because that is really, really key for electricity. You're going to learn today what happens when electrons move. You're going to know why materials are either a conductor or an insulator. And you're going to know how static charge is different. Exciting. Don't need to write this down. We'll just bear them in mind so that you know what you're doing. You can check it, go back at the end to check if you want to. Now, to organise this topic, we're going to do it a little bit differently. We're going to start off with a nice big double page in your books if you've still got one, or just a big piece of coloured paper or something otherwise. And we're going to be making a mind map for this topic. So each time we do a little bit more of this topic, we're going to add to the mind map. So this is our central part, it says electricity, and we've got a space next to it for charge. That's what we're covering today, which is charge. And then we've got 1, 2, 3 more spaces around it for later on. So you can draw that now, or you can, and then we'll add to it at the end of the lesson. Of course, while you're drawing it, you may want to pause the video. Quick reminder, we looked at this in the beginning, a different way in the table. This is one of the diagrams you often see for an atom. You've got our nucleus here with your protons and neutrons together, and you've got little loopy bits which are called shells, which is where your electrons move. And all matter is made from atoms. Absolutely everything, whether it's a solid, a liquid or a gas, all made from atoms. And they have 3 types of particle that exist together inside the atom. You don't find them separately. Protons are positive, nice and easy, P for proton, P for positive. Electrons are their opposite, so they're negative. And neutrons, to start with an N, have no charge. N for no, N for neutron. P for proton, P for positive, electrons are the ones that are left over. But if you use the first letters, 3 letters, you've got pen, P-E-N. Easy way to remember it. Do you have your pen for this lesson? Ah, amazing, hey? A reminder for the parts of the atom now. Nucleus contains the protons and the neutrons tightly together. The electrons are small and they're in outer shells. And because they're in shells around the outside, they're not joined on, so they can move. That's really important for electricity. And the first inner shell can hold 2 electrons. And remember when we were in school, we did this with thumbs up. And you can either have 1 electron or 2 electrons in the inner shell. You don't have to have 2, you could just have 1. You cannot, however, have 3. It's like a booking at a restaurant at a table, only seats 2, you can't fit a 3rd one there isn't space. The other shells all contain 8 electrons. If you've got both your hands up in front of you now, you bend in your thumbs, you've got 8 fingers left. Easy to remember, 8 fingers, 8 electrons. And like the inner shell, it can have 1, 2, 3, 4, 5, 6, 7 or 8 electrons. You can't go more than that. You can't have 9 or 10. You've got that many, you would need to move on to another shell, a bit like having another table in the restaurant. And each shell is filled up before another one starts to fill. You don't have one partly filled shell, another partly filled shell. They fill from the inside out. It's a bit like being at a stage show. Everyone wants to be near to where the action's happening, whether it's a play, whether it's a performance. And most electricity involves electrons moving. That's why we're learning all about electrons. Little bit of revision now. You get your periodic table, has little boxes like this for every element. This is a copy of the box for boron. It's got a capital B, which is a chemical symbol. It's got the word boron underneath. You've got 2 numbers. The small number is the atomic number. The bigger number is the mass number. Remember, the mass number is the more massive of the two numbers. And sometimes the mass numbers have decimal parts because there's different versions of the element. You round it up to a whole number. So we'd use 11 here. Look at your diagram here. You can see you've got neutrons and protons in the middle. You add these up together, that will give you your 11. Now we can see we've got 1, 2, 3, 4, 5 electrons around the outside, and the electron number and the proton number are the same. So if there's 5 electrons around the outside, 5 protons in the inside, that's shown by this number here. That is the 5, the atomic number, how many protons. You have 11, take away 5, that will leave you with 6, which is how many neutrons. It doesn't matter if the neutron and the proton number are different because they don't have charges, they don't need to balance each other out. It is the protons and the electrons that have the charges. If you need to check that over, have a pause, have a think, play it back to make sure it's clear in your minds. Now we're going to look at charges and forces. This is not charges where you pay money. It's not charges where you rush at something and try and knock it over. It's a charge as in whether something is positive or negative. We already know lots about forces. We did that earlier this year as a separate topic. I think it's January time we did that. We know about electrostatic force, which is a non-contact force. It means the two items that the force works on do not need to be touching each other. And it is very similar. Charges work in the same sort of way that magnets do. If you have opposite charge, a plus and a minus, that is like north and south of the magnet, and they will attract each other because they are opposites. If you have two things the same, two minuses or two pluses, they will repel each other. That's like trying to push the two norths or the two souths of different magnets together. You actually get quite close and then they push in opposite directions. Not the same force, but it works the same way. And all atoms are neutral because they have an equal number of protons and equal number to the number of electrons. They balance each other out. And the protons and neutrons are in the nucleus. They're close together, as we saw in that diagram. So they can't move easily, but the electrons in the shell can move. And that is how important for electricity. Now we're ready to begin our new learning. Now that's all clear. Now, if you want to see electrons moving, well, you can't see individual electrons, but you can see the effect of lots of electrons moving. There's a really cool piece of equipment. We have it at school, and we'll try and get it out for you in September. It's called a Graaf Generator. And this is a way that you can generate some electricity. You can see the effect of the electrons moving. Now, I can't do it with you. You're at home. You don't have a Graaf Generator unless you're amazingly lucky. I know I don't. But what I have done is put in a clip, and this will show a Graaf generator in use in a museum in America. It's similar to making lightning indoors, but safely, and it's a little bit hair-raising. I think you'll see what I mean when you watch the video clip. I will put the clip separately onto Go for Schools and Teams as well to make it easier for you to see it. Okay, now we've got a little bit of revision. Also, a couple of slides ago, we've got a table to draw out and a question to ask. If you have two negative charges, will they attract, repel, or neither? Two neutrals, again, an electron and a proton. Oh, you're going to have to check what charges these particles have here. An atom and a neutron, check the charges. Something that's a plus ion, a minus ion. Don't worry about the word minus, look at the charges. And look at the charges here, a 3 minus and a 2 plus. Now, you're going to need to copy that table, complete it, and submit it to me on Teams or via email. Okay, so you will need to pause the video while you do that. Okay, conducting. This is not conducting like an orchestra. Sorry, all you budding musicians out there. This is conducting charge. Electrons involved in charges are those in the outer shell. That makes sense. They're on the outside of the atom, so they're the easiest to be influenced or reached. In most atoms, the outer shell can hold up to 8 electrons. Yeah? Metals are on the left-hand side of the periodic table. We already know that. And they've only got 1 or 2 or 3 electrons in their shell. Because they've got 8 spaces and they've only got 1, 2 or 3 of them full up, it's actually relatively easy for them to lose these electrons. Now they don't just get lost as they wander off like they're in the shops. They can be given to another atom that wants to gain electrons. We don't make or lose matter, it just moves around in the universe. And if they lose an electron, they get a positive charge because it's negative. They've lost the negativity. And metals are also able to share electrons with each other. These 1, 2 or 3 in their outer shells can move around quite quickly, and they can move between atoms, and they can fool all the atoms nearby into thinking they've all got full shells just because they move really quickly. A little bit like when you're running away from your mum trying to avoid bedtime when you're little. It can feel like there's loads of you. And those are called delocalized electrons because they're moving around quickly. They're not joined to one particular atom. And if you have got a shell that is able to lose electrons, or you've got delocalized electrons, that will make this atom a good conductor of electricity, which is why metals are good conductors of electricity. Conductors allow charge to flow. All metals are conductors. One example is copper. Copper is used in electrical cables. If you've got some cable at home that isn't joined onto something, you can actually see the orangey colour of the copper inside it. Gold is used as a conductor in some music systems. Sure, you can work out why it's not used all around your house. Graphite is very special. It's a form of carbon which, because of the way that the atoms are arranged, is a conductor. Weird one here, salt water is also a conductor because it's got positive sodium ions and negative chlorine ions, and the charge can move between them. And your body actually has liquids within them called electrolytes, which actually will conduct small charges. You'll learn more about that in year 9. And you may have had a poorly tummy and needed to take some powder that gets mixed up with water, and that contains electrolytes to balance your body back up to being healthy again. Now, insulators are the opposite of conductors. They are non-metals, and their shells are full or very nearly full. So they've got 6 or 5, 6 or 7 electrons, so they need 1, 2 or 3 more to be full up. And it's quite easy for them to fit another one on. It's much easier to gain 1 or 2 than it is to lose 5. They do not have delocalized electrons. Their electrons got too many there for them to move around. And because of that, they do not conduct electricity. And the opposite of conducting isn't non-conducting or unconducting. It's called insulating. Please notice it's OR, not ER. Okay, little typo there. Okay, all gases are insulators because the particles are too far apart to transfer a charge. You have to be near to each other to transfer a charge. A vacuum, which is a space that has no particles, such as in space, they are also insulators because there are no particles to transfer the charge. Now there's one little weird group of elements we're looking at down here. Elements that are in group 4 in the middle of the periodic table, and hydrogen are unusual because they've got 4 electrons in their outer shell. And that means that sometimes they can behave like a conductor, other times they behave like an insulator. And that makes them a little bit tricky. Now, this is your home task for this week. You are going to be conductor and insulator detectives. You need to look around your house and find some electrical appliances. There's things that plug in. It could be hair straighteners, it could be a mobile phone, it could be a computer, it could be a microwave, it could be a washing machine. Your mums would love it if I said do all the washing, but that's not what I'm going to say to you. I would like you to have a look and see where you can spot conducting or insulating materials being used. Which part of the appliance? Why have they chosen to use them there? You can take some photos or you can draw these and you can add some notes about your ideas. You can submit this to me on Teams or via email, but do be careful. If you're going to look at an appliance, make sure it's unplugged before you investigate it. If it's a wired-in appliance such as a cooker, please be very careful. Do not switch anything on and then touch it. That's not a good idea. Now finally, static charge is a slightly different one. This is a charge that does not move. Static actually means not moving. Sometimes you can go on holiday to stay in a caravan that is in one place. It's not when you pull behind your car. That's called a static caravan. Static means does not move. But if you have two insulators and you scrape them together, the electrons on the surface cannot move and flow. But when they build up enough, they will jump towards the Earth. And that is seen or felt as a spark. You might have seen it when you've got an electric shock. Now here there is a link, which again I'm going to post onto Teams and onto Go for Schools, and it's called John Travoltage at the top of the page when you click on it. It's a simulation. There's two parts that you can be moved by clicking and moving your mouse. One of them needs to be moved first. What happens when you do it? Now I want you to investigate this. I want you to find out what happens. I want a sentence submitted for your answer, which will include the word electron, charge, transfer, build up, static. Not necessarily in that order. I'm nice, but I'm not that nice, Year 7. Remember that. Now finally, we're going back to the mind map we had at the beginning. We've got the word electricity in the middle. We've got charge over here. I would like you to add 1, 2, 3, 4, 5, 6, 7, 8 words around charge. They might be just coming off like legs of a spider, or they might join on to each other. You might, for example, have atom and then have proton, neutron and electron all joined to it because they're parts of an atom. You've got conductor and insulator. You might relate those to one of the particles. You've got static. You've got to decide where to put these. This is for your notes and your understanding. Oh, sorry, I didn't want to add any text to that, just trying to get rid of the box. So, hopefully, this is another interesting lesson. So we can't give you a lot of practicals to do with electricity at home, but we're going to try and find a simulation for building some circuits for next week. If you've got any questions, email me, message me, or message the whole class in posts on Teams, and have a good week. And I might even see some of you at school this week. Take care, Year 7. Bye for now.